We're going to finish up our last problem with osmotic pressure. Under osmotic pressure pushing up on me. So that's a nice little pun if you're a David Bowie fan. Anyways, or a Queen fan. Working at Bell Labs, first transition is electronic structure of glass and magnetic materials were discovered. Investigating nylon 66, so this structure right here. Different solvents, which can be utilized to perfectly reflect certain wavelengths of visible light. Camouflage equation for octopus camouflage. So we're running an osmotic pressure experiment. We choose the plot below at room temperature. So here, temperature equals 298 K. So let's see what we're working with here. We have a plot of reduced concentration here. So we know our master equation, the pi divided by C2 as a function of C2 will give us our first virial expansion coefficient. It will have the form of P over C2 as a function of C2 equals A1 basically times C. But if we reduce that, actually we have this C1 or C2, excuse me, plus A2 C2 squared, and we know that A1 is equal to our first virial expansion coefficient. So let's look at our lecture 6, our kind of key fundamental expression. Where is it? Where's our master equation? Right here. So this is our first virial coefficient, so A sub 1 equals RT over Mn, and our A2 is this. So it's this whole mess, but really we only care about one thing, this 1/2 minus chi. So that is going to be kind of the slope again that we're dealing with. So let's go back to the exam. So if that is in our A sub 2, so our A sub 1 equals RT over Mn, our A sub 2 is equal to this basically 1/2 minus chi. So if this is our kind of function, we're reducing it by this reduced temperature versus C. Our y-intercept is going to be this A sub 1. So each of these is our A sub 1, our first virial expansion coefficient, and the slope here is going to be actually horrible. So our slope is going to be this A sub 2. So we already know if our slope is positive, what are we dealing with here? So if chi is greater than 1/2, we are in a what type of good solvent, bad solvent? So if our chi value is greater than 1/2, we are going to be in a bad solvent. And then we are going to have our slope is going to be negative. And we can look back and examine that in our lecture 6 notes right here. So if our slope is negative, chi is greater than 1/2, poor solvent, bad solvent. And then if we have our chi is greater than or less than 1/2, chi is equal to 1/2, our slope is going to be 0, and we're in a theta solvent. And finally, if chi is less than 1/2, we are going to be in a good solvent, and our slope is going to be positive. So here, for blue, we are in alpha greater than 1. For red, we are in theta, and for green, we are in alpha less than 1. So we've already kind of deduced a lot of what's going on here. So let's answer some of the questions. So where does the solute move when you place the polymer in the tank? So remember we had this tank here, we had polymer here, solvent. So again, solvent mixes, solvent moves to the left, they go to the polymer side. Why? To increase that delta S of mixing, your configurational entropy. Again, what drives the solute motion is the thermodynamics, it's this delta mix, it's this osmotic pressure that kind of causes that to flow. When will the solute stop flowing? What is this energetic condition? Well, it's when the solvent flows here, our kind of pressure, osmotic pressure, our volume in that little kind of tube raises here, it decreases here. Eventually, the osmotic pressure, that driving force equals that, gravitational force, stops flowing, and that is when the chemical potential on this side, 1, is equal to the chemical potential on this side, this 0 side. So you can go back through the notes and kind of read that out. What do we have to be careful about when we're running this experiment in terms of concentration of our polymer? Well, we have to make sure, again, that we are in this kind of really, really important scenario where we are thermodynamically concentrated so that we are greater than our overlap concentration, but that we are mathematically dilute. So we have to meet those two conditions simultaneously. again, that's what we talked about previously in lecture. Yeah. So, what is the degree of polymerization in each experiment? How will N scale with R to 1/2 in each solvent? How can you tell? Explain in terms of the master equation. What gives you solvent quality and excluded volume? So, let's deal with how is N. So, we have A, B, and C. So we just said for in terms of solvent quality alpha, and then we want to see how N scales as well. So we said for A, we're in a good solvent, so greater than 1, 0, less than 1. So how can we tell? So we know that N, if it's greater than 1, N to the 3/5, N to the 1/2, N to the 1/3. Good solvent, bad solvent. And again, we reduced that from that master equation, which, again, remember back in lecture 6, we kind of said that we have in this master equation here, this this value here tells us about our contact interactions, or right here. So this gives us our contact interactions or solvent quality with a chi, and then here, this just gives us our excluded volume effects. So, and this whole term here is called the excess chemical potential. So the excess chemical potential here gives us our solvent quality, excluded volume. When those two equal out, when there's no excess chemical potential, we recover our ideal conditions. So that's, again, what we've discussed about previously. Excellent. How can we tell? Obviously, just from our slope. So which has the higher degree of polymerization? Well, we know that this slope is RT over Mn. We know that R has units of joules per mole K. This has moles of, or units of K for temperature, and then it's grams per mole for our degree of polymerization. So this cancels, this cancels, this cancels. Pascal, we should know, is Newton per meter squared. If I'm multiplying by meters cubed, that's a Newton meter over gram. So a Newton meter is a joule, joules per gram. Everything's working out. So if I want to find the degree of polymerization, i.e. my highest molecular weight, I'm just going to go ahead and plug in. So R equals 8.314. My T equals 298. And then I need to solve for Mn. So I just need to solve R times T divided by X equals, set equal to 0.03. And then I want to solve for X. So that's 1. Okay, it's this inverse relationship. So here I'm going to say it's 0.022. How about that? 0.025. And then finally, solve for here. Yeah, it looks about like 0.1. So I could see, just as again we anticipated, that the lower, again, this inverse relationship, so the lower the value, the higher the Mn, because this is fixed. So there's your degree of polymerization. And then it says, sketch the phase diagram qualitatively, chi versus Phe2 for A and B. So quick note, the solvents are all aqueous in nature, so consider that when drawing the phase diagram. So this is a really tricky question, but I really liked it. So let's kind of think about what's happening here. So for A and B, I know that for A, my chi is in a what type of solvent? So A is my blue, my slope was positive, so I know that chi is less than half, and that for B, my chi is equal to 1/2. So if my chi is less than 1/2, these A and whatever the solvent that we're in, it wants to mix. So I know that my chi curve as a function of my Phe2, again, I'm mixing with a polymer solvent, so x1 is not equal to x2. So I know that my chi curve is going to be shifted over to the left, some value here. It's going to be asymmetric, and it's going to look, something, kind of like this. So it's just going to mix at kind of these low values of chi. So like this is my for A. Now for B, and there's going to be some critical chi C. Now for B, I'm going to put this as blue, my chi is equal to 1/2. So if equal to that means it's a higher chi, like they don't want to interact. So what's, where's it going to push that critical chi-C? It's still going to kind of, same, assuming that they're same, actually they're not the same. Actually, we could really deduce this here a little bit further. So I know that for B, my red polymer, my degree of polymerization is larger. So X1 and X2 are still larger, but my X2 B is greater than my X2 A. So I know that that's going to shift my critical one a little bit more to the left here. So it's going to shift to the left there. And what's going to be the critical chi parameter? Is it going to be easier to mix or harder to mix? Well, in A, they really liked each other. Like that, that polymer really liked the other polymer. So they are going to want to mix. So it's going to be easier. I can mix at higher chi values. Why? Again, because chi is proportional to 1 over T. So if I can mix at higher chi, I can mix. Higher chi means lower temperatures. I can mix at lower temperatures. But if they don't want to mix, that chi is going to shoot down a little bit further. And it's going to be lower anyways because of this, this higher degree of polymerization. So it's going to shift to the left, and it's going to move lower that chi-C. It'll be asymmetric like that. Now, nylon 6,6. When you're in an aqueous solution, so all these solvents are aqueous in nature. If you're in an aqueous solution, these amide linkwages can form hydrogen bonding. So that might form mixing here initially. So you want to be careful. You might have a scenario where you're, again, so here we're mixed, then we're demixed. You can have that basically lower critical solution temperature like we've seen previously. So you could have another region at the top here where you flip again. So you're mixed, demixed, and then at higher temperatures, we might demix, or excuse me, actually, for chi, you might have a region below here where we're basically mixed again. So at higher and higher temperatures, i.e. lower and lower values of chi, you might demix again. So you might have that lower critical solution temperature. So that's just a little caveat. So again, it's kind of easier to visualize if you look at temperature versus phi2. So we know temperature versus phi2, we had, it'd be the same kind of scenario. So my blue curve would be much higher in terms of temperature, and it would look shift to the left. My red would be a little bit lower, and like this, again, asymmetric. But you might have a scenario where, again, demixed, 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 mixed. You might have a scenario here where you could be mixed and then demixed again. So be careful of those lower critical solution temperatures. So that was a hard question, but a fun one. Some people got it last year, so hopefully you'll do the same. But that's it. So I'll see you all in the review session, and good luck on your exam. I know you'll do great. Thanks. Bye.